你要把 t 跟 t square 看成那个 pt，应该六 t 等于零，三六 t 等于零，对对 t 等于零。哦，什么是手写六 t 等于 t？对，我把 e 等于 pt 了，嗯，pt 等于一，哦，pt 等于一，因为 p 那个还是 e 嘛，p 也是 e，p 二个是 e。嗯，零等于一，空图片 t 等于零的时候，p 零的 pt 等于一个方程是 constant 的，在每一个点都是一，换位置。OK，让给你看 pt 等于 t，这样 t 等于一的时候是多少？对吧？然后 p 等于二的，这个一样，这个是说每一个 t 它都是一，一零的时候是一，一的时候也是一，什么 t 它都是一，它是 constant 嘛？比如说 fx 等于一嘛，这样你在每个 x 啊就一样，对不起，嗯，对，对，它后面的题是招风者，然后影响只差前面那个发生。就是那个问题改了，哎，没有，哦，这个是第六版的，哎，确定第六版，哎，就是我还真不是，我抄错了。OK，不过这个是这一个的答案，对，嗯，因为有人来找过我也是，这个呢，这个对吗？这个是对，这个是错的，这个应该不是哦，是，这个是第一跟第三，错， Testing. Testing. Okay, good morning to everyone. This is the last early class we had for this semester. This early class always remind me of school camp. So school camp, we usually have event until night and then sleep and then morning wake up, event again. So it's basically like this. And then we have continuous classes like Tuesday, Wednesday, Thursday, every week. And intensive. Um, Also, I plan to take a group photo today before we take the quiz. Is it okay? Yeah. Because I think today is the most full attendance because of quiz. So maybe we can take it today. Yeah. Um, so we will do it before quiz later, and then let's dive into the question for this morning. In the tutorial, I'm not sure you have done this question or not. Previously, I put a wrong answer, and then I change it already. By the way, there's a lot of mistake in lecture 5, 6, and 7. I mean the tutorial solution. So check the updated version one. Okay. When people told me, I will adjust it. So please check out the latest one. And then if you found any new mistake, just let me know again. And then we'll keep updating. Okay. So if A is diagonalizable, then A is invertible. So like this, how to attack this question. So first you need to know what is diagonalizable, what is invertible. Okay. So first of all, when you see this word, right, go and find definition first. Okay. If you don't understand definition, then you come and find me. Or if you cannot find the definition, you come and find me. Okay. After you found the definition, you should read. So what is A is invertible? A is diagonalizable if there is P and D such that A equals to P D P inverse. P is diagonal. Okay. And then what is A is invertible? That is if there's this A inverse such that A inverse equals to identity or the other way around. Okay. So you have PDP inverse. How do you get A inverse? Okay. So my first guess is I can take A inverse, okay, of PDP inverse. Okay. Because we assume that we can write it as PDP inverse. So this is what I have in my first mind. And then I get P, what's this? P inverse, P inverse, right? that right? Right. Okay. So my first thought is, okay, it is invertible. Okay. So it turns out it's wrong. Okay. So which part is wrong? Okay, let's think about which part is wrong. So P inverse should be fine because at first P and P inverse already exist. Okay. So it turns out the problem is the diagonal here. Okay. So diagonal here doesn't mean invertible. Okay. So when we didn't spell out the definition of diagonal. This is the part that's have problem. So a diagonal matrix. So this part got problem here. So a diagonal matrix is a matrix with 0 in the of diagonal. Matrix don't care what is in the diagonal. It cares about what is not on the diagonal. Okay. So for example, you could have 6, 0, 8, and then 0, 0, 0, 0, 0. As long as all the other thing outside diagonal is 0, it's diagonal. Okay. So in this case, this determinant of this matrix is 0. This example matrix. What's the determinant? What's the determinant of this example matrix? 0. So it's not invertible. Okay. So this is the part that goes wrong. Okay. So the answer is false for this case thing. Okay, because of the diagonal matrix. Okay. Okay. Yeah. The next question is a lot of you send me messages, ask me about algebraic multiplicity and geometric multiplicity. Okay. I think I also go really fast that time when I introduce these two numbers here. So if you want to know about algebraic multiplicity, geometric multiplicity, so multiplicity means a number. So algebraic is an adjective. So algebraic number. So it should be number belong to something. Okay. So actually, when you talk about algebraic multiplicity, you should say algebraic multiplicity of, because this is a number belong to something. Okay. When we talk about algebraic multiplicity, it belong, so algebraic multiplicity of an eigenvalue. Geometric multiplicity of an eigenvalue. Okay, so it is something that related to eigenvalue. Okay. So whenever you ask this kind of question, right, you need to go back to and find the definition. Okay. So which is the lecture? Can someone remind me? What's the lecture for eigen stuff? Okay. So for example here. What's algebraic multiplicity? Okay, they define it in a bit convoluted way. Okay. It says that if you have this polynomial here, if this power to the k divide the polynomial, but the extra power doesn't divide the polynomial, then we take k as the algebraic multiplicity. Okay. So how to read this definition here? So we look at this example here. Okay. So for example, in this character polynomial, right, we already factorized into 3 roots. Okay, first one is 0 root, 6 root, and -2, right? All right. So let's ask about algebraic multiplicity of 0. Okay, what's the algebraic multiplicity of 0? Okay. It says that if lambda minus 0 to the k divide PR, but lambda to the 0 to the k plus 1 doesn't divide, then we take k. Okay. So for example, lambda 4 divide characteristic polynomial, but lambda 5 plus 1 doesn't divide. Sorry, lambda 4 plus 1, which is 5, doesn't divide. So we take 4 as the algebraic multiplicity. Make sense? Okay. For example, let's say we say, okay, lambda, lambda, lambda to the 3 divide, right? Lambda to the 3 divide. But lambda to the 4 still divide. Okay. So we don't take 3 as the algebraic multiplicity. Make sense? Okay. So that means what? That means the algebraic multiplicity is the power of x minus lambda inside the characteristic polynomial. So algebraic multiplicity is something related to character polynomial. Is the x minus lambda, how many times it appears in the characteristic polynomial. This is algebraic. Why is it algebraic? Because it's coming from a polynomial. Okay. Is that okay? Algebraic coming from polynomial, characteristic polynomial. The power of the root. Okay. Is it clear now? Clear? Okay. So next is a geometric multiplicity. So geometric meaning something to do with geometry. So what kind of space you are looking for? You are looking for the eigen space. Where's the definition? Seems like the definition is hiding somewhere. Okay, actually, there's a definition at the back, but I also put it here together with algebraic multiplicity for you to like compare. So geometric multiplicity of eigenvalue is defined to be the dimension of the eigenspace. Okay, I think still have some of you cannot convert between eigenspace and null space of A minus lambda I. Okay, these two is the equivalent things. Okay, eigenspace is a space that where you have AX, the X equal to lambda X. Okay, but to solve AX to equal to lambda S is the same as solving A minus lambda I and X. Okay, so it becomes a null space of A minus lambda I. Okay, so one thing you need to remember is eigenspace of lambda is equal to the null space of A minus lambda. Okay, this you have to always remember. Okay, null space of lambda I is how we find the eigenvector using row reduction. Okay. Do you still have question on algebraic multiplicity and geometric multiplicity? Skip this one. Any more questions on geometric algebra? Okay. Maybe later we will do some more diagonalization before doing your quiz. Okay. Okay. Before we go into chapter 7, yesterday, somehow remind of this example here. We skipped this example, by the way. I put it as a exercise. So can you quickly examine whether this A is orthogonal set or not? The column. Are they orthogonal? Can you quickly examine whether it's orthogonal for the column of the column vector? Is this orthogonal? Column of A, are they orthogonal? There's no trick question here. Are they orthogonal? No, right? Because if you take the inner product, you get 1. It is not 0. Okay, so this question asks you to find a least square solution to the inconsistent system. Right? Already told you it's an inconsistent system. So you still want to have the solution, but there's no solution. So they call it a least square solution. So you need to project your B down to the column space of A. Right? To do the projection, what is the condition you need on the vector you have? Still remember? When you want to do projection, what is the condition of the basis you need to do the projection, to use the projection formula? Anyone recall? What is the condition on the basis so that you can do inner product and then compute the coefficient? What's the condition on the basis that you need before you can decompose your y into using the inner product method? Anyone can recall? Anyone can recall? What's the last topic about? Chapter 6. What's the topic of chapter 6? What's the topic of chapter 6? Huh? Orthogonality. Okay. So we have to start with an orthogonal basis. Let me bring the statement up. Okay. Maybe not this statement, maybe a more stronger statement. So there's a key thing here. So you need to start with an orthogonal basis. Okay. Only with this orthogonal basis, you can use this formula to project your y. Okay. If it is not orthogonal, then this y dot u1 thing doesn't work. Okay. You have to start with orthogonal basis. Okay. So every time when you want to do this kind of projection, right, make sure you start with orthogonal vectors. So what does this mean? So since this is not orthogonal, right, you cannot directly project your B onto these two vectors, okay, because they are not orthogonal. So if you still want to project on column of A, what do you do? What can you do? If you still want to project on column of A, what can you do? Can you make them into orthogonal vector? Can or not? Give you a basis, can you make them into orthogonal vector? Can. How? How? Huh? How? 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 How to make basis into orthogonal basis? Huh? How? What's the process you learned yesterday? What's the process you learned yesterday? How to make an orthogonal basis into how to make a basis into orthogonal basis? What's the process you learned yesterday? What's the name? Grant? Grant Smith. Okay. So you can take your A, okay, apply the Gram-Schmidt process to make it into okay. So how to do Gram-Schmidt? Today we won't do it yet. First, you can try at home, and if you have problem, then tomorrow we can discuss again. Okay, Gram-Schmidt. So how to do Gram-Schmidt? You fix the first vector first, right? And then you project the second vector onto V1, and then take the difference. Okay, so you project down and then take the difference, become orthogonal. Project down, take the difference. Okay. Then you can do the projection on V onto orthogonal vectors. Okay. So since this one is so troublesome, so maybe you can use the A as hat equals to A, B to solve it. Okay, instead of going through, there's two ways here. First way, you can make it orthogonal and then project. Row reduce, find the solution, or you can solve ATA x equal to AB. Also can. Okay, two way. This is the last thing we learned yesterday. Okay, any question? Any question? No? No question? Okay. So tomorrow plane, okay, I haven't done today, but I want to talk about tomorrow plane. So tomorrow plane, we will finish the last most important working or calculation is called the singular value decomposition. Okay, there will be one question on that thing. If we finish earlier tomorrow, maybe we will do one summary on everything we learned, and then we will discuss quiz, and then that's all. Okay, so today we will learn symmetric matrices and quadratic form. There's only 3 sections of this chapter. Okay. So first, we still want to diagonalize. Okay, but this is a special form of matrix where A transpose equals to A. Okay. So if A transpose equal to minus A, we call it anti-symmetric. But it's not important, but we just deal with symmetric for now. So since what time is it? 42827. Okay. Since today we have quiz on diagonalization, maybe we also start with a diagonalization exercise now. Okay. So the matrix now, can you recognize that this is a symmetric matrix? So when you transpose, it is still the same matrix. Can everyone see it? If you transpose it, if you do the transpose, it's still the same. Row become column, and then row become column. Everyone see it? Everyone see it? Okay. So, or the other way to see it is along this diagonal, right? It is symmetric. That's the way to see it. Okay. So let's give you some time to diagonalize this matrix. So I give you about 10 minutes. Okay. So after 2 minutes, I will release solution answer for eigenvalues, and then 2 minutes eigenvectors, and then you can check whether you diagonalize it correctly or not. Okay, let's do this exercise here, and also will help you for later. Let's try diagonalize this. Usually there's no quick way to compute determinant. So you just need to go all the way. Unless the matrix is really nice. There's a lot of zero there or cancellation. Otherwise, you need to expand it. So sometimes maybe computing determinant might be a pain. That's why you will see the textbook sometimes they just ignore the step and then give you the final answer. So make sure you know how to get to the final answer. They're also being lazy because it's tedious if you put everything down. But make sure you know yourself how to compute. Yeah, you just compute and then see if you get the same answer as actually I got the answer from the textbook saying that. Let me see. Got this, I think it should be correct. But somehow I didn't get it. Does anyone finish calculate the characteristic polynomial? Anyone finish? Is it same as this one? Is same? Okay, then it should be correct. Yeah. So you guys can keep continue if you got the characteristic polynomial. And so if you want to diagonalize this guy, right? Actually, this turned out to be harder. So usually how you do it is you found the first root first. After you found the first root, and then you divide that root. Okay. So this first root, I think, turns out to be 3. So it's quite hard. Maybe I just tell you how to decompose this, and then you use it to find your eigenvector. So it is 8, 6, and 3. Okay. Use this 3 number to compute the eigenvector. Like 6 and 3. So usually in exam, right? Usually, maybe 0, 1, or -1, or 2, -2 will be the first root. Okay. Usually this number will be tested first. But anyway, take 8, 6, and 3 as the eigenvalue, and then try to diagonalize this. Find the eigenvector. Anyone got the eigenvector already? Is it the same as here or you got different answer? Same. You can shout out if you have different answer and then we will see. Is it same? Okay. So from here you can see that the algebraic multiplicity of the eigenvalue 8, 6, and 3 is all 1, right? Because the power is just 1 in the characteristic polynomial, okay? And the geometric multiplicity is also 1 because they span by 1 eigenvector, right? Okay. So actually there's one more property between these eigenvectors here. So you can actually see that they form an orthogonal set. Try and check their inner product. They actually form an orthogonal set. Can you try? Try inspect. So this one with this one, you get minus 1 plus minus 1. And this one with this one, the 8. And this third one, you have minus 1, 1 as well. And then this one, you have minus 1 plus 2 to 0. Okay. So it turns out that the eigenvector from the symmetric matrix form an orthogonal set. Okay. So what do we have here? So we have here that pick P to be 0, 1, minus 1, 0, minus 1, minus 1. P equals to 8, 6, 3. We can diagonalize A. So if you want, you can perform normalization to the matrix. So you can make it a length 1 if you want to make an orthonormal basis. Okay. So it turns out that if A is a symmetric matrix, then any two eigenvectors from different eigenspace are orthogonal. Okay. So there's a special thing about this symmetric matrix here. Actually, when I preparing the quiz, right, I was thinking how to combine the orthogonality and the eigenvector. I was thinking like what matrix that can give these two together. But after I didn't manage to think of it on top of my head. So after I designed the quiz and then I prepared for chapter 7, I only found that, oh, symmetry matrix is what I want to do for. Because I was thinking to combine these two together. So maybe ask you to check whether the eigenvector are orthogonal or not. Yeah. So it turns out that symmetric matrix will do the work. I will do it next time. Okay, but this theorem here, we won't prove it, but just give you this example and then you try to remember it. This is an example. This is the property of a symmetric matrix. Any two eigenvectors from different eigenspace are orthogonal. So next theorem is this. So I think I should define orthogonally diagonalizable first. Okay, let's define this before we talk about this theorem. So definition, and n by n matrix, so as a square matrix, A is said to be orthogonally diagonalizable. Okay, diagonalizable you already know. Okay, so what does it mean by orthogonally diagonalizable? That is, if there exists an orthogonal matrix P such that P inverse equal to PT. Okay, this is the definition. And a diagonal matrix D such that A equals to PDP or PDP inverse. Because the nice thing about orthogonal matrix is the inverse is just transpose. Okay, you don't need to go over Cramer's rule or the determinant of 2 by 2 matrix. The good thing about orthogonality is you transpose it, then you get the inverse. Okay, this is why we like orthogonal a lot. So you don't need to go to the Cramer's rule, do the core factor as mentioned, find the inverse. You just transpose it, you get the inverse for orthogonal. Okay, so it turns out that if a matrix can be orthogonally diagonalizable, which is what we did just now, it turns out that the original matrix must be a symmetric matrix. Okay, and only symmetric matrix can be orthogonally diagonalizable. Okay, so if and only if and only if. Okay, so this is nice thing about symmetric matrix. Okay, any question? Any question? Maybe we take a break here if no question until 8:59 and then come back and continue.
Sure. Still some
Yes.
space.
Okay. Second space of
是这里。
水，还有 space of 水。你是说这个是 A 减某些 lambda I 哈？那怎样？
就是在那个点当中，一定是这个，我可能是这个，
这样的？不可能哦，
不能这样。
就是你这个不是一个其中可能性的答案，
就是没有，
没有可能性，因为你这个的意思是说它是没有 trivial solution，所以它不可能是其中一个eigenvector，
就是不能在那个
它一定要有，它一定要
那个
一定要有 trivial，这样的话它才有
哦，对
trivial solution，
对
对吧
，OK。
哦，OK，不用紧，叫他 email，
哦，明白一点。
他有好几个都是冷水可以，因为他们是还好的是阳的，
他今天早上就说出来，
呀，还有其他同学也是这样，我会一次过不同时，他发邮件给你，
对，
那他还在一房了，啊对，OK，我会联络他。
OK。这个解释没有在看你，就是这一步到这一步是怎么出来的？
对，全部人都在问这一题，不然等下我也再讨论一次。OK，回去那个题目看一下。OK，第一步你要知道这个 T 怎么作用在 P2上面。OK，然后OK，你是不知道什么叫做 matrix or relative 这个，还是你不懂怎么看？
不是，这就是单纯的就是这一到这一步是就在这个一完题就一分。
对，哎，其实这个答案还没有结束。
对，
啊，对，还没有给
可以讲。
解一半忘了，还是可以看出来，但是还没结束。其实，哦，可是你说你连这个也看不懂，怎么回事？
我这一步就
OK，好好好。 我给你听，你看他说啊，把这个 P 啊放去这个东西，OK，然后这个意思是什么？如果放所有的 P 在里面，你就要算 P 零出来，算 P 一出来，算 P 二出来，OK，所以这里算了三个东西，一个是 PT 等于一，一个是 PT 等于二，一个是 PT 等于 T 数，然后如果 PT 比如说 PT 等于 T 的话，那 P 零等于是不是等于？PT 等于 T 的话，你知道 X 等于 X 的话，X 等于零的时候是2，这个一样的东西。如果 你看 PT 等于 T，T 一等于多少？不，Fx 等于 X 的话，F 一等于多少？一啊，所以 PT 等于 T 的话，P 一等于一哦，PT 跟 Fx 一样的，它就是 substitution 那个 substitute 那个 T 的，对对，对，
用空间还是说用几何？
那个
这个 style 用几何证还是说用那个
用 algebra 算，用 algebra 算，但是我这个写的是它的几何的意义，
我昨天没搞
你绝对没有搞出来，
写个，
我帮你写一个，这个书里面没有吗？
没找到。
嗯嗯，第一个哈，对不对？
对，
哦，诶，真的有点危险哈，我想一下，OK，
U 等于 UT 乘 U 这个 V
这个这样子对不对？对吧？什么叫为什么？没有，这个是定义 d o p 它的定义，记得吗？诶，这是哪一个？这不是在 I 吗？这个活在 I 呢？这个活在 I 呢？I 呢？活在 I 呢听不懂
U 乘
啊？对，RM，所以什么问题？没有问题，不是，我可以拿 transpose，可以啊，可以啊，可以啊，对，
对
然后干嘛呢？OK，然后下一步可能是你要知道的东西，它应该是这一个东西，如果没有记错的话，这个是你要证或者你要知道的
这好
呀。如果你有了这个，这个就 identity 了，然后就，哎，你先不要跑先帮我检查一下这个，你帮我检查一下这个
检查那个 UX 的 T 的这个应该是性质。
第9课，对吧？嗯，这些练习做很赶，6点几了，他那个是在 lecture 9，这个，所以这个 matrix 就是这个，我想确认一下，希望你 B 等于对，是不是等于1减1，1，0减1，2跟0减1，10吧？这样就对。
题就是它那个题在这里，就是
那我最好做工这边呢，这个是对哦，
就没有答案是
还没有改。
false。对，
你看，我又自己加一个条件进去，所以这个第几题？ 这就是
Factor 12的，
应该要跟昨天一起改掉的。
对，就那个男的，
因为之前我不知道那个 orthogonal，我忘记掉。
是可以
有弄
zero，
对，在哪里啊？第24号。
对。
Okay, another most asked question from you guys is this question here. This tutorial question here. You want to discuss this before we continue? Huh? This one? Okay. Yeah, let's discuss this. Actually, I just found out that my solution is not finished yet. Unfinished. Yeah. It's actually unfinished for part C. It's actually unfinished. Okay, I realize that the notation may be very new to you guys, so you don't make sense of the arrow. Maybe after today, you will know it. Okay. So first read the question. The question is quite short, just a few words. So define a T map. It doesn't say whether it's linear transformation or not, just a map. By Tp equals to P0 minus P1T plus P2T squared. Okay, maybe look at this first. Okay. So actually it assumes you about function. Okay. How about if I change this to function, will you be more familiar? Let's say if I put Tfx equals to f0 minus f1t plus f2t squared. Okay. So for example, let fx equal to x squared. Okay. So what is Tfx? What happened to x squared? Huh? So first is what? Substitute x to be equal to 0. Okay, so you got 0 squared minus 1 squared times t plus, sorry, maybe to be consistent, I put t here. So become 2 squared t squared. Is it clear or not? Or still confused? Okay, I think some of the confusion maybe come from this t and the. Okay, some of you maybe come from this t, and this t. Any confusion between these t? No. Just ask, because I don't know where's the confusion, so you need to tell me if you're really confused. Because I don't know where's the confusion. Does anyone still have confusion on how to do this? Okay, maybe we give another example. So let gt equals to 2t plus 1. See where this t set t plus 1, 2. Okay. So t applied to gt is equal to t applied to 2t plus 1. Okay. So first you need to replace your t as 0. So 2 times 0 plus 1 minus, then second one is replace t by 1. So it's 2 times 1 plus 1 times t plus 2 times 2 plus 1 t squared. Anyone still don't know how to substitute or not? Does anyone following? There's no trick here. Yeah. If you're confused, you should speak up because I don't know where is the confusion. Is it okay, everyone? Okay. Okay. Yeah. Okay. So this is how this function here works. Okay. So you substitute your variable as 0 or 1 or 2. Okay. So first, it asks you to show that it is a linear transformation. Okay. So we didn't really emphasize on this, so you can just take my word here, or you just disregard also can, because actually we don't introduce linear transformation for abstract vector space, but it is not too hard to generalize from the Rn case. Okay, so if you want, you can read. If you don't want, never mind. But the key part is actually B and C here. Okay, B and C here is the more important part. So B here, it says find TP when PT equals to this. Okay, so substitute this function, whether this is an eigenvector or not. So to check something is an eigenvector, what do you need to check? What's the definition of eigenvector? TP equal to eigenvector satisfy what? TP equal to lambda p. Okay, so you just compute TP. Okay, so if you compute PT, see whether it is a scalar multiple of P or not. Okay, so you apply TP. For example, 2 minus 2 plus T. So first you substitute the 0. Okay, let me copy this map here so that I can compare. Okay, so now T become minus 2 plus T. Okay, so when T equals 0, minus 2 plus T become minus 2. Okay. When T equals to 1, minus 2 plus 1 is minus 1. And then when T equals to 2, minus 2 plus 2 is 0. Okay, or a bit too fast. Let me move. So let's compare these two equations. So maybe I move this one to this guy. Okay. So something like that. So this one, first one, second one, and third one. Can see it? Can see it? Okay. Okay. So what we get in the end is minus 2 plus T. Okay. It turns out that in this case, it is easy to see. It's just P itself. Okay. So what we get is TP equals to P. So what's the lambda? TP equals to P. What's the lambda? 1. Okay, so it's an eigenvalue 1, eigenvector with an eigenvalue 1 here. Okay, make sense? Okay. There's no trick here. If you're confused, you should ask. Okay. Any question or not on how to calculate, on how to read eigenvector? I can explain again if you want. Any question? No? No? If you want, you stop me later also can, if you're still thinking about it. Okay, third one is find the matrix for T relative to the basis for P2. Okay, what's this asking about? Remember yesterday we have the example on change of basis? Okay, so this question is actually asking about if you express your vector in terms of this basis, right? Okay, actually I need to tell you how's that? Some truth here. I think we don't learn this part. This is an extension on what we learned. It is like the question 8. Actually, it's like this question here. It's a bit like this question here. But how to say? Okay, never mind. Okay, let me draw the picture that you cannot understand again. So when I see this map, right, I like to turn this map into this picture here. Okay. So I have two space and then I have a map between them. Right? This is what the question giving. Okay. Then this question say give a matrix relative to the basis. This is the motivation that we did last time. Okay. What do I mean by that? So I'm gonna say something that maybe doesn't make sense to you, but see if you can make sense of it or not. So relative to basis, to this basis, right? What we can get is the coordinate vector. Through this coordinate vector, remember that we said that P2 is isomorphic to R3. Everyone still remember? Okay. Given a basis, and then if we take coordinate vector, we have an isomorphism between P2 and R3. Right? Because n-dimensional vector space, I'm going to say some alien word, maybe seems alien to you, but actually it's what we learned 2 weeks ago. Okay. So because we got this isomorphism between these two space. Okay. So what is it? The matrix here asking about is actually the matrix going from here to here. Okay. If you don't care about this concept, right? Let's say I throw away all the concept. What is TB here? Okay. What's the TB asking here? So the TB asking here is actually something that add on what do I call P? PB equals to TPB. Okay. If I throw away all the concept, what is C? What is this question C about? The concept, the question C about is finding the basis relative to the basis, meaning you need to find a matrix such that when you add on the coordinate vector of P, you get the coordinate vector of TP. Okay. So P and TP live up here. Okay. So whenever I put this thing, right, this is for element, this is for space. So space is just an arrow. Element, I will put something like a fish arrow, hook arrow, fish arrow. Yeah. Okay. So how to do this? How to do this? Okay. Okay, if you still don't want the concept, okay, throw away how to do this. So how to do this? How you do this is you check where the basis element gets sent to. Okay. So you start with checking where the basis element gets sent to. Okay. To find the matrix for T is to find where the matrix gets where the basis element gets sent to. Okay. Does it make more sense now? Find where the matrix basis element gets sent to by T. Okay. So let me put it here. So see all the bases B1 get sent to TB1, B2 gets sent to TB2, B3 gets sent to TB3. Okay? Is it? Okay? Okay. Yeah. Yeah. If you don't want to go into the concept, but just to do what to do, if you see this kind of thing, you just compute what is happening on the basis element. Okay? And then you extract the coefficient out. You extract the coefficient out. Okay? For example, in this case, we got B1 minus B2 plus B3, yeah, equals to B minus B2 plus 2B3, and then equal to minus B2 plus 4B3. Okay? And then how to get the matrix? How to get a matrix? How to get a matrix? So what's the matrix that you apply to B1? You get 1B1 minus 2B2 plus B3. How to get a matrix? Okay, let's say I give you this question here. Okay, I give you this question here. How to get a matrix? How you get a matrix? Get a matrix. Okay. Okay. To get a matrix, you just get the coordinate vector. Thing going on here. So for this short time, you just remember what we need to do, and then after that you can figure out why we want to do like this. So how to get TB is just coordinate of TB1 and then coordinate vector of TB2 and then coordinate vector of TB2. Okay, this is by definition. This is by definition. Okay, this is by definition. If you don't want to like know what's going on, you just use this definition here. Yeah, actually I want to say one thing. There's a lot of things happening behind this definition. Okay, if you really can go and understand it, you will see a very beautiful and constructed theory. If you see it. If you don't see it, then just memorize this formula. Okay. If you don't see it, you just try this formula. But I really want you to see what is happening behind this formula. Because it's really like patched together. Maybe you don't understand what I said, but please take my word. Okay. For now, if you can't understand, never mind. At least you know what to do first. Okay. So take that definition. If you want to find the matrix relative to B, take this definition here. Okay. What you do, you need to compute T on the basis element and then take the coordinate vector. Coordinate vectors. Okay. So in this case, the TB here is what? Okay, let me move this. What time is it? 9:18. Okay, so can you get the coordinate vector from just looking at this TBI here? Do you know how to do it? You know how to do it? Okay, so I will say the answer, see if you know. If not, just voice out. So TB1 expressed in terms of B is just 1 minus 1, 1. And then TB2 is 0 minus 1, 2. TB3 is 0 minus 1, 4. So you just pick up the coefficient on B1, B2, B3. 1 minus 1, 1, and then 0 minus 1, 2, and then 0 minus 1, 4. Okay, so this is the TB you want. Okay. Yeah, just stop me if you learn. Okay, yeah, good. So how do we get TB1 equals to B1 minus B2 plus B3? Okay, so since we already know where TB1 gets sent to, okay, we want to express this polynomial here in terms of B1, B2, B3 again. Okay, you can see that T applies to 1 is 1 minus T plus T squared. You see it? T applies to 1 is 1 minus T plus T squared. Why? Why? Okay. So why? So why you need to start with this map here, T, this linear transformation. So T sent any PT to P0 minus P1 times T plus P2 times T squared. Okay. So when PT equals to 1, what is P0? What is PT equals to 1? Meaning for every T, the value is 1. So what is P0? 1. Okay, so we got a 1 here. What is P1? 1. So we got another 1 here. What is P2? We got another 1 here. So T1 gets sent to 1 minus T plus T squared. And then we express this in terms of basis again. Because basis is what we can express every linearly, every vector uniquely, right? Okay. So it's the first basis element minus the second basis element, and then plus the third basis element. Okay, so this is how I get B1 minus B2 plus B3. Okay, so you notice that there's no B1 here because all of them are 0 at the constant term. Okay, how about the rest? The rest? Any question from the rest? So really the answer for this question is to figure out this TB here. Figure out this TB here. Okay. So to compute this TB, you need to know what happened to TB1, TB2, TB3, and then take the coordinate vector. Okay. Any question? Any question? Any question? More question? Okay. All right. Let's continue first. If you have one last question, maybe we do it before the quiz. Okay, next. So just now we stopped at orthogonal and a square matrix is orthogonally diagonalizable if and only if A is a symmetric matrix. So we spend 1 hour doing one question, not 1 hour, I mean half an hour. So we diagonalize a symmetric matrix and where we found that the eigenvectors are actually orthogonal to each other. Okay, so which we call the orthogonally diagonalizable. Okay, so next we will call. So maybe we skip this example where we leave as homework or provide solution to check. Okay, next. So next before we go into this spectral theorem, let's introduce a new word here. So take a definition. So the set of values of a matrix A is called the spectrum of A. Okay. So next time, if you heard about spectral theory or something like that, it is most probably has something to do with eigenvalue stuff. Okay. So the set of eigenvalues, you collect them together, we call it a spectrum of A. So spectral theorem has this following statement. If you start with a symmetric matrix, okay, you would have n real eigenvalues. Okay. Adding up the multiplicities. And then the dimension of the eigenspace for each lambda is actually equal to the algebraic multiplicity. Okay, so that's mean the GM and the AM, geometric multiplicity, and the algebraic multiplicity are the same. Okay, for symmetric matrices. So if they are the same, that means you can diagonalize it. Okay, moreover, it is orthogonally diagonalizable. Okay, and the eigenspaces are mutually orthogonal. Okay, so this is a nice thing about symmetric matrix. If you have a symmetric matrix, it will enjoy these properties here. Okay, so it's always diagonalizable. So next part is spectral decomposition. So if we write into PDP inverse, what's the big deal about this PDP inverse here? Okay, so the big deal here is the inverse here is the transpose, right? Okay, so it is a transpose of the P. Okay, so when you really compute the matrix multiplication here, right, you realize that actually you are doing inner product. Okay, so when you expand out this matrix here, okay, you will get lambda 1 u1 u1 t, and so on. Okay, do you buy this or you want to see example? Do you buy this? Do you buy this? Hello? Do you buy this? No. A equals to PDP inverse. You can write it as a form as lambda 1 times the first column and then multiply with the first column transpose and then so on. And this is what we call a spectral decomposition. Remember what happened to U1? Okay, never mind. So yeah, this is instead of U1 T U1, right? It becomes U1 U1 T. Yeah. How about try on this example here? Okay, let me try this example here. Okay, let's try C from this example here. Okay, so I do a little bit of cheating here. where I already found all the eigenvalues. If you want, you can check on the spot. Let me start with this color here. Okay, so so first, if you want to do spectral decomposition, you will orthogonally diagonalize this matrix here. Okay, orthogonally diagonalize the matrix. So what do you do first? You go and get your correct polynomial lambda I. Okay, and then you will find out that lambda is actually equal to 8 or 3. Okay, and then you will find the eigenspace or eigenvector for different lambda. Okay, so first one you will find is probably let me see, it is 2 divided by square root 5, 1 divided by square root 5. Okay, and then second you will find is v lambda equals 3, which is minus 1 over square root 5, then 2 over square root 5. Okay. Maybe you'll see that maybe you'll think that this basis is not nice because divide by square root 5. Maybe you want to multiply by square root 5. Actually, they purposely do it because they want to normalize this vector. If you compute the length, it is just 1. Okay, so they divide by square root 5. So by the theorem, by previous theorem, we can write A equals to PD P inverse, or just PD P transpose, because it is orthogonal matrix. So I'll write square root 5 over square root 5 minus square root 5, and then 2 over square root. Okay, so what's the D? D, you should align the eigenvalue with the position of the column vector, which is their eigenvector. So, so as what I said just now, for 2 by 2, for inverse of an orthogonal matrix, you don't need to go through the Cramer rules, or you need to go through the determinant, the inverse formula. You just transpose it. So you get 2 over square root 5 minus 1 over square root 5 over square root 6, 2 over square root 5. Sorry, it's 5. Okay? Okay? Okay. Okay. So what's going on here? So this is the PDP inverse thingy. So let me continue. So the claim is A is actually equals to lambda 1 of V here, V lambda 8 square multiplied by V lambda 8 transpose plus lambda 2 V lambda 3 and multiply lambda 3 transpose. Okay, so this is the claim of the spectral decomposition theorem. Okay, this is claimed by, so this is claimed by spectral decomposition theorem. Okay, so this is claimed by spectral decomposition theorem. So let's just check. Let's check whether it's true or not. Okay. So, what is lambda 1? Lambda 1. What's lambda 1? Yeah. What's lambda 1? 8. Okay. And then what is V lambda 1? V lambda 1. So it's this vector here. Copy this. And then you multiply by the transpose. And then plus lambda 2 is 3. Okay. 3 times V lambda 3. V lambda 3 is minus 1 over square root 5, 2 over square root 5. And then multiply by the. Okay. So what's this? A 2 times 1, 1 times 2, you got a 2 by 2 matrix. You got a 2 by 2 matrix ready. So what's the first matrix here? What do you get? 4 over 5, 2 over 5, 2 over 5, 1 over 5. Right? Okay. And then on the other side, you get 1 over 5 minus 2 over 5 minus 2 over 5 and 4 over 5. Okay. And then you add these two up. Add these two up. How to add? So you get 32 over 5, 16 over 5, 16 over 5, 1 over 5, plus 3 over 5, minus 6 over 5, minus 6 over 5, 4. And then what do you get? 35 over 5, 10 over 5, 10 over 5, 5 over 5. Okay, which is 7, 2, 2, 1. Okay. So which is is it wrong? Wrong again. Let me see. Oh, okay. Did a mistake here. So there's an 8 here. So 8, 12, 12. Okay, here I forget to multiply some more. So here is actually 12. Here is 20. Here is 4. Okay? Yeah. Okay. So so what does this mean? So this means that this means you can decompose your matrix into summand on eigenvalue. Okay, so you decompose into sum of products with eigenvalues. Okay, yeah. So you split your A into the summation of matrix multiplied with the eigenvalue. So this is called the spectral decomposition. Okay, maybe I don't know what is going on here, but maybe let us go to the next one. For now, it's just not much info. Just write A in a different way. Okay. Yeah. Okay. So what is important here is you look at this part here. This part here. Okay. This part here. U1, U1, T. So next, we introduce the quadratic form. So what's the quadratic form? So it's everything looks like xt times the matrix times x. Okay. So you will see that this is very much like inner product on Rn. Okay. Inner product is what? Inner product is so the inner product between x and x in Rn is xtx. Okay. So meaning you can slide one identity matrix in the middle. Okay. But now we can put any symmetric matrix in the middle now. Okay. Symmetric matrix in the middle. So with this A is a symmetric matrix put in the middle. Identity is also a symmetric matrix. So that means inner product is kind of a quadratic form. Okay. Okay. So now we change this identity here to any symmetric matrix. Okay. Maybe in a moment we will see what kind of a geometry happening in a quadratic form. Okay. But let's say we want to write down the quadratic form defined using A. Okay, let me show you. So the first one. So let's write down the quadratic form defined by A. Okay. So what is this quadratic form here? So you will see that this Rn, right? Rn here really depend on what A you have, or the A will depend on what N you have. So since this is a 2 by 2 matrix, right? So this is a 2 by 2 matrix. This X should live in R2. Okay. So where is living in R2. Okay. So this X should be general X. So we can write it as S1, X2. So if we put back into the formula again, St is x1, x2 become a row vector multiplied by A and then multiplied by the column vector x1, x2. Is it okay? Is it following? Still following? Okay. So now we put A into the formula. So if some space. So here we got -2, -3, 6, and then x1, x2. Okay. So what do we get from here? So what we get is 2x1 minus 3x2 minus 3x1 plus 6x2. Okay. And then row times column, what do you get? We get, let me make a bit. Okay, so what do we get? We get times 2x1 plus 3x2 plus minus 3x1 plus 6x2. Okay. And then we will get 2x1 squared minus 3x1 x2 plus, sorry, minus 3x1 x2 plus 6x2 squared. Okay. So this is the quadratic form we're looking for. Is it okay? Okay, so try for 2 minutes, try and compute the quadratic form for B. See if you can find a quadratic form for B. Yeah. Try if you can find the quadratic form for B. This is quite important because later we'll do a reverse process. Yeah, try for 2 minutes. Okay, see if you can compute this. X transpose times B times X. So first of all, you should ask where this X live in. Where should this S live in? R3. Okay, because your matrix is a 3 by 3 matrix. So you should write your R3, your X in terms of X1, X2, and X3. You want to finish computing this? finish computing this? Anyone? What do you get? What do you get? Minus x1 plus s1 square plus s7 s3 square. Okay. So you will found that actually for diagonal matrix, right, this computation is easier. Okay. You just multiply the diagonal with x1, x2, s3 squared. Okay. So this is one observation we have. And then the next one is, the next example is, it gives you the quadratic form, okay, and asks you to find the A. Okay. Can you do that? You given a quadratic form, how to go back to A? How to go back to A? Try see from this example here. Okay. So try to find the link between this coefficient and the number inside this matrix. Okay. So for example, for the previous example, the A matrix here, you'll see that the 2 and the 6 appear on the square term, x1 square and x2 square. Okay. This one I haven't finished compute, right? This one should be 2x1 squared. Let me make it smaller. So this is a 2x1 squared, x1 squared, minus 6x1, x2, plus 6x2 squared. Then the 3 here contribute to x1, x2. Okay, so, okay, let me draw some diagram here. So 2 minus 3 minus 3, 6. Okay, so if you label here x1, x2, x1, x2 here, the number inside the matrix will reflect the coefficient on the product of this xi. Everyone see it? So for example, this 2 here will reflect the coefficient for x1 times x1. And then 3 here will reflect the coefficient of x2 times x1. And then minus 3 here will reflect the coefficient of x2 times x1. And then 6 will reflect the coefficient of x2 times x2. So can you try and figure out what is A here? Okay, try to figure out what is A, then we will take a break and then we will go into quiz. If you can't, yeah, only can find A, then we can take a break. And what is A? What is A? First of all, what is the size of A first? What's the size? 3 by 3, right? Okay, because we have x1, s2, and s3 here. So it's a 3 by 3. So what's the thing inside there? What's the value inside the entries? What's the size of the entry? Sorry, what's the thing inside the entries? Or maybe you tell me what is on the diagonal first. What's on the diagonal? 5, 3, and 2. Good. Okay. How about on the off diagonal? Well, off diagonal, what should you put? So what's the thing below 5? Huh? What's S1, S0? Okay, wait. So tell me what's the first column? Don't know? You don't know? You don't know S1, S2 is what? What do you mean? S1, S2, you mean? You mean this spot here? Oh, you don't know what is this? Do you know what is this? Also don't know. Anyone know? -1. Okay, wait, let's try. So this is -1, and then 0, and then how about second column, do you know? 0, 3, 8, and then 0, 0. Okay, let's see this example, this solution, right? Okay, to write into a quadratic form, what A have to satisfy? Symmetric. Is this matrix symmetric? No, right? If you transpose, it's a different matrix. So how do you split the coefficient? Huh? 1/2. Okay, so that means you need to split across the. So you make this into -1/2. You make it into 1/2. How about this one? How you split this at 4? Okay, so you split into 4 and 4. Okay, and then use this matrix. Do the STAX again. See, you really get this QX. Okay, so check whether QX is equal to X T A. Okay, and then you should get what you want. Okay. Should we go a bit further? And let me see. Let me see. Okay, maybe I don't want to torture your mind again. Just let you see something nice, and then tomorrow we will talk about it. Okay, so why we study this quadratic form? So quadratic form have some examples. So for example, this guy here. Okay, so if you look at z equals to x 3 times x1 squared plus 7 times x squared. This is a quadratic form. Why? We can write it as xt times a times x. Okay, so this is a, what is called, this is a cone. Okay, you got a cone facing out, or you can get a folded, folded plane, and then you also can get a saddle. You know what saddle is? The thing you put on the horse when you ride the horse. Okay, you get something like a saddle, and then you also can get some cone facing down. Okay, so we split this. You can see that the term here. Okay, one thing you can see that is the 0 point is always get sent to 0. Okay, because if you replace S1, S2, S3 to 0, you just get 0. So 0 is always get sent to 0. You will notice that. Okay, so we always achieve this 0 point here. But the problem is about how about the other point? Okay, sometimes you will see that the point are always positive. Okay, for example, the first one. Second is There's along a line it is 0, and then for the rest is all positive. Okay. And then how about saddle? Saddle. So you got positive, you also got negative. Okay. And then this cone facing down, always negative. Okay. Notice this. Find the relation between this positive, negative number using the coefficient here. Okay. You can see that when the coefficient is always positive, the value you get is always positive, not for quadratic form. But if your coefficient of the quadratic form is negative, then the value you get will be always negative. Okay. If you have a mix of positive and negative, then you also get mix of positive and negative. Okay. This is something to observe here. And tomorrow we will review the secret why it is like this using eigenvalue. Okay. So the value depends on the coefficient. This is not always true for general polynomial, but for quadratic form, you can see it. Okay, any question? Any question? Okay, maybe let's take a break and then later we come back for group photo and then quiz. Okay. 10:05.
有点懵。
哪一个？
没看你之前的笔记哦。
哪一个
那个是什么？关于 quiz。
？quiz？什么 quiz？
那一课咱们那个变换。啊，
对，
这里我也想问。
对，
这里我能把这设成，我把它设成 A0加 A。
可以。
这样写出来，我觉得会就是看起来显然一点。
给我想一下啊。哦，如果你要写成 A0啊，
P 设
这个好像那天有谁告诉我，有问过我这个问题。假设 OK， 这个其实跟这个是一样的。然后这个就是去到 A0，
减
掉 A1 T，
不减 A0减掉 A0加
1加 A2 T。
A0 加 2A 加 4A T。
对，
就这样写看起来显然一点，
可以，
明显一点，
也可以。
那奇奇怪怪的东西，是就是OK， 我画一下，这样画一下，就是这样的那个东西。我是不是这一步它本身不可以表示成一个矩阵，它要通过这样来表示。所以说写出矩阵的其实给的矩阵都是这一步的矩阵。
对，就看你什么。
我有点懵，就是有的什么时候该拆，什么时候该
拆的，
就是 lecture 11的题目。就这里是把它拆成那个什么拆，
对，
然后对，把它合起来，那就是什么时候该给的，什么时候该少。
听不懂。
就是我怎么判断他给的那个矩阵是这一步还是这一步？
其实都可以，其实你可以这样画，也可以这样画，只是重点是看你这个怎么上下嘛。上下不重要，你也可以把它画在下面，然后第一画在上面，都可以，就是都可以，但是你就要知道你的箭头怎么来去就可以了。重点不是那个，重点是这边左右的 space。
左右
它重点是这个左右的 space， 而不是上或下的问题。其实上下是没有问题的，因为我们这边是 invertible， 所以我们可以往上又可以往下。
那
重点是左右是发生什么事情？
左右发生事情
对，
怎么看？
怎么看呢？就是我们通常either是 change of basis 过后，我们找到这个 D， 或者说就是我们找不到，我们要用这个 D 来表示 T 的 matrix 的表达式。
就是他给我一个矩阵，他跟我说就是从 A 到 AX， 那我怎么知道它是什么意思？
没有什么意思，它就是这样。
那然后呢？
它就是这样。
然后他现在让我求这个变换在对应的一个 B 的 B 为基的那个。
所以你意思说你这边要有两个空间先？两个空间过后，它可能 change of basis 过后换去同一个空间，但是不同的 basis 的表达形式，然后你才找得到这个 B 这样子哦。可以明白吗？就是把所有东西放去新的 basis 来看过后，which is 那个 coordinate vector， 那这个变化就变成一个不同的、比较简化的或者是不同。
那就那道题啊，
哪一道题？
那个就是在下面那个。这题，他虽然是告诉我 A，然后让我求在以 B 为基的那个。
对。
那我为什么要拆？那我是不是直接把 A 转到 B 的形式来表示？把 A 拆成两个列项量，然后把这两个。
对啊，这个就是 D 的找法。喂，给我想一下。对，
不是
没有错。你透过你讲的那个东西应该是一样的吧？我觉得。我觉得是一样。我觉得是一样。
那这个含义是？
这个含义是我不要透过你那个，我去透过 变化来算。我透过变化来算，而不是去算那个 a b 1啊 a b 2啊，然后算它的 coordinate vector。
但是我那样算出来答案不一样啊。
不一样吗？等一下查一下，我等一下查一下，我等一下查一下。这不考，而且大考也不考，syllabus 也没有碰。Hello，
Hello, testing. Any last question before the quiz? Last question. Last question. Okay, actually, I add up just now. Zhangzhou point out this. So there's another form of writing this map here. You also can express your PT in terms of basis first, and then write out what coefficient you want to keep. Okay. This is another form to write this map. Actually, someone came to my office last week also mentioning about this. Jinhao, is it Jinhao? Or someone? I forgot. One of there's two come to my office last Friday, and then they also mentioned about this form here. Yeah, these two are equivalent form. Depend on situation. Maybe one is easier than the other. Okay. Okay. Can the right and the left, you guys move to the middle so it can take photo in the middle. You don't need to bring your stuff. You just your person move here. Move to the middle, and then we take photo in the middle. So those. Luckily, I got a friend here, so maybe I can ask my friend to take it. Yeah, just move to the middle. Yeah, no need to bring stuff. Later you have to recall back. Yeah. Yeah, need to bring your bag. Later you will return one. Okay, are you done? Yeah, thank you. Stand in the back. Not enough seats, stand in the back. Yeah, okay. Don't hide yourself. Hey, so okay. Okay.
等下啊，可以了，那坐过来一点，然后这边坐过来。OK 啊，可以。1, 2, 3。可以。
Freestyle.
Freestyle。
可以 freestyle。第二个。
1, 2, 3。OK。
Okay. First person. Okay, go back to 6. First person, please tell me to count how many in your group, and then into 4 groups. We'll do the attendance. Yeah. Yes, it is. Four. 24 no 他没有考啊，他不是11哈。Oh good, 3% no. Yeah. If you need extra paper, you can get from here. Don't start first, you can read. Not good, so you will see some red line. Don't start yet. Just read first. We'll start together. Everyone got already? Okay, no iPad, no calculator, no laptop, as usual. Scientific calculator can. No phone, no iPad, no laptop. Okay, before we start, first question, if you don't have enough space, right, you can write at the bottom of question 4. I believe question 4 don't need much. Okay, if there's anything unclear on the question due to the extra black line, you should point out. If no, then we will start 10:12 and then we end at 10:42. You get some. You need more time? More time? Okay. Another 5 minutes. Okay, 1 more minute, right? Clean up your solution. Sure you write down your name and ID. Okay, hands up. So check your name and ID. Pass your solution to the front. Help me check if there's enough Please pass to the fund now. Pass your answer to the front.
Yeah, yeah.
Pass in front. Sign your attendance. Make sure you sign before you leave. Sign. 11. 11. Okay. Before you come to the lecture tomorrow, right, please have a look on for the singular value decomposition. Okay. Tomorrow we will value to understand. Never mind. At least see the stack, what is going on. Then tomorrow I will explain what is going on in details. Okay. Hey, if that's all, see you tomorrow. Okay.